Hi, I'm Dominic, and in this video I'll demonstrate how our query profiling and visualization tool can give us insight into query execution. Understanding query execution in a complex distributed database is key to identify bottlenecks and improve performance. Our tool has already helped us to identify, understand, and resolve performance issues in Myria. I'll demonstrate this tool with a simple triangle query that joins the same relation and then takes the output and joins it again with the relation to produce the final output. When we run this query, it takes about 16 seconds to run. I enabled the query profiling, and we could query the recorded data, but in this demo I will use the query visualization tool. In the visualization, we have the physical query plane on the left, and on the right we have an overview over the whole execution. At the top, we can already see that one problem could be the large number of tuples that had to be sent during the execution of this query. Below, we have a time series visualization that shows for each fragment, which is an execution unit that runs in parallel, which operations executed when. For example, we can see that fragment 1 to 4 mostly finished within the first 2 seconds. Only one worker continued up until about second 14 to run. Let's examine this long tail a little bit further. In this view, we see a breakdown of which operations contributed the most to the running time of this fragment. Details are available on demand. Below, we have the time series view as before, where we can select a range, and a detailed view reveals exactly which operations executed on each worker. We can look very closely into this execution. We can see that the shuffle producer calls the join, which calls the left and the right shuffle consumer. Let's zoom out again to see what happened in the long tail. If we scroll down, we can see that worker 58 continues to produce tuples up to about second 14. To understand this, let's go to the communication view. This view shows a matrix of how many tuples were sent from which worker to which worker. Let's sort this by the number of tuples that were sent and received. We can see that worker 58 received more tuples than any other worker. This could mean that there's a very popular join tuple which had to be sent to worker 58. To confirm this hypothesis, we will look at the communication after the join. And yes, we can see that worker 58 produced a lot of tuples, which then had to be sent to different workers in order to be joined again with the other relation and then stored on disk. A solution is the hypercube shuffle join, where tuples are sent into hypercube and then joined locally in a multi-way join. Fewer tuples have to be sent, and the computation is evenly distributed over the available workers. To wrap up, our tool provides insight into query execution, which helps identifying bottlenecks. Different perspectives on the log data provide different insights and together provide a whole picture of how the query was executed in a distributed database.